In AC circuits, most relevant quantities, like voltages and currents, resemble sinusoidal waveforms like this. And at first, this seems perfectly fine. For simple situations, like this circuit with only a resistor, the maths is very neat, where a sinusoidal voltage yields a sinusoidal current which is perfectly aligned. But for most real circuits, where we have things like capacitors and inductors, the maths quickly gets complicated. For example, in this simple RLC circuit, the voltage drops of each component as a function of time look like so. And as you can see, this looks rather messy. However, these three waves, summed together, yield this very simple sinusoidal curve, which would be our voltage input in this example. But I certainly wouldn't have blamed you if you couldn't see that just by looking at it. Similarly, if we wrote out the three functions for these graphs, which are all sinusoids, you'd probably have a rough time crunching the numbers to show that the sum of these is equal to the input waveform equation. Overall, maths involving many sinusoidal waveforms quickly gets complicated. And this is of course unavoidable when learning AC electricity. It turns out, however, that there exists a beautiful shortcut for dealing with waves like this. Instead of tracking how things change with time, we can freeze time and completely forget about it. This allows us to represent each waveform with a simple static arrow known as a phasor. Using phasors, we'll see that problems like this instantly become simple and visually intuitive. In this layout, it is obvious to see how these three waves might sum together to the total voltage. So in this video, we are going to go through phasors from scratch. We'll find out exactly what they are, why we can use them in AC circuits, and exactly what they're useful for. Let's begin. To start with, we're going to forget this example with resistors, capacitors, and inductors, and in fact forget circuits altogether. Instead, we'll just think about waves in general. Suppose we have a single oscillation, a simple sine wave like so. This wave has an amplitude A1 and angular frequency omega. So, the equation is simply A1 times sine omega t. There's nothing complicated here. This wave just continually oscillates like this forever. More generally, a wave has three components. The amplitude controls the height of the wave, the frequency controls how quickly it oscillates, and we also have the phase shift phi, which determines how much the wave is offset along the x-axis. For a single wave, this doesn't really matter, but when we have multiple waves, the phase shift is essential. So let's suppose we have another wave. This wave is oscillating at the same frequency omega, but it has a different amplitude, which we'll label A2, and it's slightly out of step compared to the first wave, so it has a phase shift, which we'll label phi2. Our goal is to somehow simplify each of these waves into something more intuitive to visualize and work with. It turns out that there's one feature of AC electricity which allows us to do something beautiful. The frequency of all waveforms is fixed in a steady-state AC circuit. In other words, once the circuit is in equilibrium, every voltage and current oscillates with the same frequency, no matter how complicated the circuit is. If you are curious, this frequency is fixed by the AC generator. Either way, the bottom line is that the frequency is not something that distinguishes one waveform from another. So, out of our three variables, we can completely ignore it. Our AC waves therefore only have two parameters, the amplitude and the phase shift. What else has two dimensions? A simple 2D vector. This vector, known as a phasor, can perfectly represent our sine waves. It has a length equal to the wave's amplitude, and an angle equal to the phase shift. Here I've plotted the phasor for the first wave, where the phase shift is 0, so the phasor sits on the positive x-axis. We'll define these axes in a moment. If we rotate this vector anti-clockwise like so, its height on the y-axis perfectly traces out our sine waves. If we plot our second wave, with a different amplitude and phase shift, it is drawn on the graph like so. The tail of the vector always sits at the origin. Once again, if we play our animation, it traces out the second waveform. But technically, we don't even need to worry about time here. When we rotate our two vectors, you can see that they stay in the exact same positions relative to one another. Because their frequencies are the same, time is completely irrelevant. We can fully recreate our waveform as long as we know the amplitude and the phase shift. So why are these phases useful? Well, it turns out that there are some truly brilliant mathematical shortcuts we can take when writing sine waves like this. Any phasor with a length and an angle is in fact also a number. Specifically, it is a complex number, which has a real part and an imaginary part. The real part is the x-axis on this graph, while the complex part is the y-axis. The complex number, which we'll label j, is the square root of -1. Now I'm aware this probably seems like a huge jump, so let's break down why we can do this. If you're not familiar with complex numbers, they are literally just numbers with the square root of -1 in them. But they are also two-dimensional numbers. A real number, like our first vector, which has no rotation, lies flat on the real axis. This only has a real part, which we'll label b1. When we introduce a complex part, we are effectively rotating our vector. Our second phasor has a real part b2 and an imaginary part c2. Let's enlarge it so we can clearly see what is going on. The real and imaginary parts relate to the amplitude and phase shift in a very simple way. The real part is simply a times cos phi, while the imaginary part is simply a times sine phi. If we wanted to convert a complex number back to its sinusoidal waveform, we just need to find the magnitude and the angle. The magnitude is simply the square root of the real part squared plus the imaginary part squared, and the angle is simply tan to the -1 of the imaginary part over the real part. You can easily derive these results yourself using our previous relations if you're not convinced. Using this, our waveform is simply the magnitude times sine omega t plus the angle. By the way, if we want to reintroduce the time variable into our diagram, we can simply add omega t to the angle. When we show only the phase shift, we are effectively setting time to 0. So the angle at any time is omega t plus phi. When we do this, the real part becomes a cos omega t plus phi, and the imaginary part becomes a sine omega t plus phi. So as you can see, reading the imaginary part of our phasor, with omega t included, is another way of obtaining the waveform. But writing our phasor like this exposes another useful trick we can use. If we write out the complex number in terms of the amplitude and phase shift, then factor out the amplitude, we get in brackets cos omega t plus phi plus j sine omega t plus phi. This can be expressed in a much simpler form, that is e to the j times omega t plus phi. This is Euler's theorem, a truly beautiful piece of mathematics that, if you're not familiar with, I'd recommend looking at the many great videos out there on it already. But with this, we now have an extra way of writing our waveform. Overall, we have 3 ways of expressing our wave. Firstly, in terms of our amplitude and phase shift, which we can neatly write like this. Secondly, as a complex number written as b plus j times c, which, in terms of a and phi, is just a cos omega t plus phi plus j sine omega t plus phi. And finally, we can write it as an exponential, a e to the j omega t plus phi. So why is all this useful? When calculating AC circuits, we regularly have to add, subtract, multiply, divide, differentiate, and integrate sinusoidal expressions. Converting our sine waves to different mathematical forms make these operations far easier. For addition and subtraction, complex number format is best because all we have to do is add or subtract the real parts and add or subtract the complex parts, which are just numbers. This is much easier than trying to add or subtract exponentials, for example. For multiplication and division, we can use polar formats where we can use the following mathematical shortcuts. If we multiply 2 phasors, we simply multiply their amplitudes and sum the phase shifts. If we divide 2 phasors, we just divide the first amplitude by the second and subtract the second phase shift from the first. It's also pretty easy to do these operations in exponential formats as well. Lastly, for differentiation and integration with respect to time, we use exponential formats. Taking the derivative of the exponential just means taking the prefactor of t out front, which is always j times omega. For integration, which is very similar, we just divide by j times omega. So with this toolbox, we now have everything we need to deal with steady-state AC circuits. These three ways of expressing sinusoidal waveforms apply to voltages and currents in any steady-state AC circuit, where the frequency omega is the same for everything. In the next video, we'll begin looking at how to solve AC circuits containing resistors, capacitors, and inductors, for which phasors will be essential. Specifically, we'll introduce a new concept known as impedance, which is the AC equivalent of resistance, as well as a more general form of Ohm's law that is exclusive to AC circuits. By the way, I will soon be releasing practice problems for this video on the free Decipher Physics iOS app, which already contains practice problems on capacitors and GCC physics. Thanks for watching.